Okay, so hello everyone. So this is Alfred Chen from UC Irvine. So I'm serving for this session as your session chair. So for this session, we're going to talk about visual sensor security. There will be 4 papers, 3 attack papers, and 1 defense papers. And then they will touch many things related to cameras, including this facial recognition, including your fingerprint, including your images, and definitely also including your keystrokes, right? So a lot of things are unified under the theme of the camera-less sensors. So the first talk is from Wenjun. Yeah, Wenjun is a PhD student in the College of Electronic Engineering at Zhejiang University. So his research interest includes sensor security and machine learning security. Wow, that's all very hot topics. And then his research focus is on the security of the sensor component of real-world machine learning systems. And this is actually the only defense talk in this session. So yeah, let's definitely cherish that. So yeah, go ahead.
Hello everyone, this is Wenjun from Zhejiang University. Today I'm going to present our work titled CamPro, Camera-Based Anti-Facial Recognition. This is a joint work with my USS lab colleagues. Human activity recognition, or HAR, is widely applied in many sectors, including surveillance, sports, and healthcare. A typical vision-based HAR system consists of a camera and a server. The camera captures user images and sends them to the server, which then uses computer vision algorithms such as person detection, pose estimation, or image captioning to analyze human activities. However, vision-based human activity recognition is often linked to privacy concerns because cameras can unintentionally select sensitive personal information, especially our faces. For instance, attackers may perform facial recognition to infer the user's identity without their consent. To protect users' privacy, anti-facial recognition technology has been developed. Most existing methods use image post-processing, such as face obfuscation, face swapping, and facial adversarial examples to protect the sensitive personal information. These methods are computationally intensive and run on servers, as they require at least one advanced visual algorithm to locate our faces. However, as the captured images are still unprotected and stored on the server, it could be leaked and cause privacy breaches. So if the camera can directly output protected images that prevent facial recognition, we can cope with the privacy issues, even if the image is leaked on the server. Therefore, we aim to initiate privacy protection at an early stage by shifting from the server-based post-processing to camera-based pre-processing. So our basic idea is privacy preserving by birth. That is to say, privacy preservation in the process of image capture inside the camera. However, most existing anti-facial recognition algorithms require intensive computation. So is it possible to achieve such goal inside a basic camera module? The challenge is that a basic camera module only consists an image sensor and an image signal processor, or ISP, which is dedicated to process the raw data into a standard RGB image. The sensor and the ISP functions are implemented in hardware and thus not adjustable. But the parameters of these ISP functions are configurable by the firmware. Typically, these parameters are manually turned by the expert during the development process. Inspired by this, our basic idea is to achieve anti-facial recognition by adjusting some of these ISP parameters. So now the question is which parameters to adjust. After analyzing all ISP functions, we found 2 functions that are suitable for parameter adjustments. They are color correction and gamma correction. Color correction is to minimize the color distortion through a matrix multiplication operation, using a 3x3 matrix as the adjustable parameters. And gamma correction modifies the image brightness to correspond to human eyes' nonlinear perception. This is typically achieved through a piecewise linear function where the y values are adjustable. So now the problem is that we can at most manipulate the colors of the entire image, not the face only. So as we protect the facial information completely, human activity recognition may not work anymore. Conversely, if the parameter adjustments are too minor, facial recognition may not be effectively prevented. So the key challenge is to maintain the utility of the HAR system while preserving privacy. Specifically, the utility has two aspects. The first is to ensure that human activity recognition can function properly after parameter adjustments. The second is to ensure that humans can view the image normally in case they need to review the recorded footage. For the first challenge, we consider an optimization problem of ISP parameters. The problem can be viewed as a three-player game on privacy and utility, where Alice is a camera module with adjusted parameters, Eve is a facial recognition module to infer the user identity, and Bob is a person detection module representing the desired HAR application. Their respective goals are indicated by the arrows of their corresponding colors. Each player can update their parameters to approach their goals. But there is an issue that Alice and Eve have conflicting goals for facial recognition, and therefore cannot be optimized together. To address this issue, we propose an adversarial learning framework for alternating optimization between protector and attacker. In the adversarial learning framework, the optimization process is divided into two steps. Step one is to update the protectors, Alice and Bob, while the attacker, Eve, remains fixed. We use the non-saturated cross-entropy loss to disrupt the facial recognition and employ the common object detection loss to maintain the performance of human or person detection. Step two is to update the attacker, Eve, while Alice remains fixed, and Bob is excluded as he cannot impact Eve. We use the cross-entropy loss to train the facial recognition model on protect images, thus forcing a stronger attacker. The optimization process iterates between these two steps until convergence is reached. The convergence is a situation where neither Alice or Eve can improve their results by updating their parameters. To conclude, the adversarial learning framework can help the protector gain robustness against adaptive attackers and gain transferability across various facial recognition algorithms. For the second challenge, we found the ISP parameter adjustments for anti-facial recognition will unavoidably decrease the image quality, even if we include a loss term or constraint to limit the magnitude of adjustments. The reason for this is the limited capacity of parameter adjustments. Here we only have two image processing, fixed image processing functions and a total of 41 adjustable parameters, which is only around 1/1,000,000th of the scale of a common deep neural network. So our idea is to later enhance the image quality on the server side, where the computing resources are not so constrained. We believe that the information on human activities is preserved on the captured images, but in a distorted way. So the image enhancement is to translate the distorted information into a form that human can perceive. We employ a UNet model as the image enhancer and train the model using pairs of captured images and the corresponding original images. The loss function is defined as the mean absolute error between the enhanced image and the original image. However, image enhancement may unintentionally restore the remaining facial information, which decreases the effectiveness of anti-facial recognition against black box attackers. Thus, we propose a new training strategy that involves masking the facial regions in the original images before training. We consider the strategy as a form of multiple task training. The loss function includes restoring the non-facial regions and obfuscating the facial regions. This enables the image enhancer to implicitly mask facial regions in the enhanced images. To sum up, the CamPro system comprises two components: a camera module configured with privacy protection parameters and a UNet image enhancer to improve the image quality. To evaluate the CamPro system, we conduct both simulation and real-world experiments on privacy and utility. First, we evaluate the anti-facial recognition performance against a black box attacker. We choose 10 facial recognition models with 2 commonly used classifiers and experimented on 2 standard face datasets. We present the face identification accuracy in this table, where a lower accuracy indicates a better anti-facial recognition performance. We found that both capture images and the enhanced images have a strong anti-facial recognition effects. For instance, reducing the mean accuracy to less than 1% on Celebrate A. The effect can be also transferred to various facial recognition models, classifiers, and datasets. We also conduct an ablation study to identify the source of transferability. We found that if the attacker Eve is not updated during the ISP parameter optimization process, the effectiveness of anti-facial recognition will be greatly reduced on the unseen facial recognition models. This implies that adversarial learning framework is a key to find solutions with transferability. Furthermore, we evaluate CamPro against the 2 white box adaptive attacks. A white box adaptive attack means that the attacker has full knowledge of the ISP parameter adjustments, which are supposed to be confidential. The first white box adaptive attack is to retraining the facial recognition models on protected images. Specifically, we conduct 40 retraining experiments. That is a combination of 10 models, 2 training modes, and 2 loss functions. The second one is to restore the original images from the protected ones. To align with our image enhancement, we employ the same architecture, UNet, to perform image restoration. Among all experiments, the highest accuracy is less than 20%, which indicates that CamPro is kind of resistant to white box adaptive attacks. Next, we evaluate the utility. We tested the person detection performance on COCO dataset and selected 2 other hardware-level heuristic methods as baselines. Compared to unprotected raw images, the average precision, or AP, on protected images is minorly decreased by 18%. But on all the detection metrics, CamPro can outperform the baseline methods. We also assess the image quality before and after image enhancement. We employ the reference-based matrix, treating the raw images as a ground truth. And we found there is a significant improvement in image quality after image enhancement. For example, the PSR increased by more than 10 dB. Let me show you some qualitative results where the magenta rectangles represents the detection results. For the capture images, the person detection algorithm works normally. And in the enhanced images, we can clearly perceive the activity of the person. Additionally, the enhanced images can be generalized to other human activity recognition algorithms, such as pose estimation and image captioning. Last but not least, we conduct real-world evaluation. We deploy the ISP parameters on actual hardware and photograph images displayed on the screen with this prototype camera. The real-world capture images are close to our simulation results with 30 dB PSR. Quantitatively, the real-world privacy protection is even more effective, and the utility is slightly lower compared to simulation results. That is probably due to the real-world noises that occur when shooting a screen. We also try to validate the capabilities of CamPro with the interface of Android camera subsystem. By modifying these 2 parameters, we successfully observed the expected visual effects, as shown on the right, on 8 different Android smartphones. To conclude, in this paper, we propose a new privacy protection paradigm that is privacy preserving by birth, Specifically, CamPro allows a standard camera module to directly produce images with anti-facial recognition effects by optimizing its ISP parameters. The effects can be generalized to various facial recognition algorithms and are even resistant to white box adaptive attacks. This is all my presentation. For more details, please refer to our paper. Thank you for your attention, and I'm open to any question you may have. Thank you.
Questions? Yeah.
Thanks for the comprehensive work. Nader Sabash, UCLA. So your image enhancer is actually in the cloud, right? It's not on the camera, like the unit. So then what's the threat model here? Because then if the image enhancer and the mask is in the cloud, then what's the difference if you just send the data to the cloud?
I'm sorry, I didn't.
So, I mean, your binary mask and UNet is in the cloud, right?
Yes.
It's not on the camera.
No.
Do you trust the cloud?
No, we don't trust the cloud.
But then where do you put the mask?
Yeah,
how do you know where to put the mask?
The mask is only, the mask is also done by the image enhancer, not by an additionally face detection model. It is a multiple task.
But you're assuming that image enhancer is actually doing it correctly, like actually doing the mask, like put the mask in the image. Because in that case, then you need to trust the image enhancer. Because if you don't trust the image enhancer, the mask would not be there in your images at all. Maybe I can talk to you offline. Thank you.
I'm sorry, I didn't very understand.
More questions? Anybody? I can ask one. So actually, I'm curious because for this one, you want to build this privacy preserving into the camera, the module itself, right? So I don't know whether you have a chance to talk to the camera manufacturers, and then I'm wondering whether they are very kind of fine with this idea, they want to do it, or there are some additional obstacles for them to adopt this solution.
Yes, we plan to actually, we haven't to contact with the camera manufacturers, but I think our method is very suitable for there because we don't include an extra hardware and zero computation cost.
More questions? So I actually know a little bit about ISP, and then in this case, I don't know whether you, I'm sure you know. So there's this new deep learning based ISP, right? So not just this kind of this, I would say, what traditional like ISP pipeline. So do you think your approach can be also applied to this new emerging deep learning based ISP?
Yeah, deep learning ISP, actually, it have a strong processor that can perform such as face detection. So in that case, our approach are not so compatible. So we want to focus on the traditional ISP where it often exists in some resource constraint scenarios such as IoT. If you have a strong processor, you can use the post-processing methods to perform something else.
Very nice. And then follow up on that. So for this one, I'm also curious about whether you think about what are the possible ways to break this specific solution. For example, because now you push all the privacy preserving this the functionality into the camera, so I don't know whether attackers will go after the ISP process now, right? So I don't know whether you have thought about are there going to be new attackers or adaptive attackers who want to target the ISP process, right? So basically, after they know all this, right?
Yeah, that is the white box adaptive attacks, which means the attacker fully know what we adjust the parameters. The white box adaptive attackers can train the model or train an image restorer to recover the benign image.
I'm actually more talking about the threat model. So in this case, maybe there are some backdoors in the camera or SP process. Yeah, because now you assume that the attacker is not like inside the SP process, right?
Yeah.
They're after. So can it go like for example, add the backdoors or something into the SP process? And in this, because this is your, so where you assume to be trustworthy, right? The SP process.
So your question is, can our approach can be viewed as a backdoor?
No, I mean like future attackers.
Future attackers?
They'll probably try to like go after your SP process now, by introducing the backdoor or.
But I think we can use something firmware verification to check whether the ISP parameters are the right one. So it's not so different, so difficult.
Sure. Yeah. Sounds very good. Yeah. So thank you, and let's thank the speaker again.